computer. Oh, close this. That's not the one I want. Oops, where is my, sorry guys. I thought I had opened the, sorry, hold on a second. Put this on pause. Resume. I apologize for that little delay. Gave everybody an extra chance to sip their coffee this morning. And okay, so I can't minimize Zoom. I don't want to minimize it. Okay, I hope you guys at least tried the assignment earnestly. If slideshow. Okay, so here was the assignment. We basically had to determine a lightest wide flange beam for the following conditions. So beam is lightest supported at every 1/4 of its span. So in other words, that tells you what the unbraced length is. The dead load was 5 kPa, and this includes the weight of the beam. I don't want you to, And the live load was 4.8. The beam has a span of 6 meters, a nice little span, 20 feet. Nice load. Now here, I want to, okay, so here basically, when I say the spacing of adjacent beams are 4 meters and 5 meters on center, what I want you to understand from here is that this is the beam we're trying to design here, and of course it's supported somehow in plan view. Here's our beam, and here's our, like, this is just represents columns that I'm putting in, and therefore in the floor plan I got another beam here and another beam here. I'm sorry, another column, and then I have the other ones there. So basically what I'm saying is that this here would be 4 meters and this here would be 5 meters, and therefore you always like you want to know how much of this floor is going to be coming to here and here, and of course that's the tributary width. And what I like to do is I like to take the distance between my beam and the next adjacent supporting member. I don't care if it's a wall, a beam, or whatever, and I like to take my beam into the next supporting element, wall, beam, okay? Take that distance and then divide by 2 to calculate my tributary width, to minimize me making a mistake. So that's what I like to do, and I find that it helps to minimize. And instead of like dividing this by 2 and then dividing this by 2 and then I'm in your head and maybe making a mistake, because if you make a mistake in the tributary width, you definitely made a mistake on the load that the beam is going to be carrying. Now, the beam is supporting finishes susceptible to cracking. What this tells you right away is that your deflection criteria has to be limited to L over 360 minimum if you want to minimize the effects of the deflection on your finishes. Then you want to determine the camber of the beam for the dead load. So once you've designed your beam, all you got to do is go calculate the dead load deflection. You'll know how much camber you can ask the guy to do it for. And of course, this is Canadian steel. And as far as the steel goes, unfortunately, this was probably an old example. I didn't upgrade to the ASTM A992 steel, but that's the steel you should be specifying. But as far as the tables go, they're all based on the lower value of the steel. So it won't make a difference if you're using the beam selection tables. So that's the criteria that we have. And now, of course, we always start by checking the combination 1, okay, and combination 2. And of course, at this point here, combination 2 is the one that will govern. This becomes our design loads because we factor them. This will become the one that we're going to be designing our beam with, or sizing the beam. That's what we mean by design and structures. Now, what is WF? WF is your factor load here, multiplied by your tributary width. And just like I showed you before, the tributary width, take the distance from your whatever you're designing to the adjacent supporting element, and then take the distance to the next supporting element, and then divide by 2, and that will be your tributary width. Now that I got my tributary width, of course, I take my I'm sorry, there's a mistake here. This should be squared. I forgot the square here, but this is kilonewtons per meter squared. And of course it ends up, so there's a little typo here. I apologize for that. And therefore my WF becomes 60.3, and I think I must have made the same tape. Yeah, I did the same typo all the way through because I simply cut and paste, and I apologize for that. So this is kilonewtons per meter squared. I hope everybody realizes that. kPa is meter squared here and meter squared there, okay? And because it's meter squared, we end up with kilonewtons per meter. So now, of course, I also want to calculate WD because I will need this to calculate my deflection under dead load, and therefore I take, and like I said, when you're calculating these service requirements, you always use the specified loads. In other words, you do not factor the loads. You always use the specified loads, and you don't factor the loads, okay? If you happen to use the factor loads, well, it's only going to be that much stiffer than when you actually need, but you don't. And if you remember, when we looked at the load combination factors, you had all the ones for strength up here where it was 1.25 and everything. And then when we looked at the load combinations for serviceabilities, all the forces were multiplied by 1.0, 1.0. That means you use these whatever specified loads to do your serviceability. You do not factor the loads. Okay, so now I've got basically what I need to do my analysis and to do my calculation. So therefore, the analysis is fairly simple. We know that if the beam is simply supported, the maximum moment is going to occur at the center. And this is the beam formula that we get from the, we get WFL squared over 8. And this gives us our MF. And of course, that's because I used the factor loads. And that's how I differentiate between my service loads and my factor loads. I always put an F whenever my loads are factored. And same thing for VF, WFL over 2. And then because my deflection criteria is L over 360, I know that this is the equation to calculate deflections for a beam that is simply supported with a uniformly distributed load going right across the whole span. And therefore, I will isolate the IX. In other words, I'm assuming I'll be placing my beam along the strong axes. And I hope you guys realize that in steel, you'll start seeing this more and more, that in steel, when we have a wide flange, any flanges, it can even be a C like this, okay? Wherever the flanges are, okay, the one that is perpendicular to the flanges is always the XX. They call this in steel, and therefore this is always your strong axis. And then this one here is your YY. They call that the weak axis. In other words, the moment of inertia about the YY is smaller than the moment of inertia about the XX, and that's why they call it the weaker axis. So now, of course, I calculate the IX required, okay? And of course, before I run to the tables, one of the most important things I have to know is what is my unbraced length. So therefore, I know that I have a span of 6 meters. I look at the geometry. I probably have 3 beams that are being supported by this beam. In other words, this will become a girder, and therefore my LU now is 1500. So the 1500 is what I need. Very important that I go to the tables with. Without this value, if you only go there with this MR value, okay, I mean, it can really hurt you, especially when the unbraced length becomes really big, okay? Now, beam selection table, well, I hope it doesn't take forever. Take a sip in the meantime. Okay, so here, guys, so basically, you're looking at least 1500. So what I do is when I come to the table, is the LU, the unbraced length that I look under to determine which beam I'm going to choose. And as you can see here, okay, so here, that means that any one of these beams would be okay because the LU is less than 1500, okay? I mean, the LU is greater than 1500, so therefore, then I look for my MR value. And would somebody tell me, what was the MR value? I don't remember off the top of my head. I'm sorry, what was the MF value that we're looking for? Does anybody remember? Or do I have to go back and?
272.4.
272?
Yes.
Yeah.
Okay, so therefore, like here, I go up, I look for 272. Well, this is not strong enough, and therefore I would go to the next page. Again, now here all of a sudden I start seeing some oh, sorry, I went up too many pages. Okay. So now here all of a sudden I see the LUs start at 2000. That means that anything in this column would probably work except for these ones here. Okay. So I look for 272. And of course, this is 278, but it's so W360 by, and then of course here I have a W, so here I have 275. So this seems to be working for me. Okay. This seems to be working for me. And of course, that's for strength. So in other words, I know that my LU that's minimum required, the maximum, or I should say the maximum unbraced length is 1,790 millimeters. I have 1,500, so I am allowed to use this value here, the MR under the bold MR here. And therefore, I just have to worry about my VR and I have to worry about my IX. And if this is greater than the IX required, I don't remember what the IX value is. I'm assuming that then this would be the lightest possible beam that will meet all my criteria for strength and for serviceability. And I don't know if you guys got the same answer, but this is, and I think that's what I chose. I'm not sure. I'm going to go back and check what I took. Yeah, I took the W46, yeah, W410 by 46, in other words, 46 kilograms per meter. It's got a nominal depth of about 16 inches. It's a fair amount, a nice size beam, okay? And of course, now the LU, in order for me to use the bold MR value, has to be less than 1,790. I have the LU 1,500, therefore I can use the MR value that's in the very first column, 275 versus 272.4. And like I said, always take the VR value and good practice, multiply it by 0.8. In other words, reduce the VR value now so that eventually if I need to put holes in the web, I will be able to compensate for that situation later on, and I won't run into a problem that, oh, I can't use this beam anymore because I'm putting so many holes that the VR value is less than the VF value, and therefore I have to go back and resize my beam anyways. So this is just to allow for the eventual fabrication and connection of your steel beam. And we will be doing connections in this course, and you'll see what, you'll get a better appreciation of what I'm saying. And again, sorry, this thing's popping up on me. So I have an IX value of 156 times 10 to the 6 greater. So therefore, this beam is stiff enough. In theory, when the people are going to be walking on it or whatever, that load of 4.8 kPa is applied to the floor across the whole floor, it should not deflect more than L over 360. Okay. And of course, if you want to know how much is going to deflect, you take that deflection equation and you put this value in, you get your WL, the live load, and you'll see what the amount of deflection would be versus what you can actually go up to. So now that I've got my moment of inertia, I can definitely go ahead and calculate the deflection under dead load. So therefore, delta D 5W. Now I just used the dead load here, and here I'm calculating deflection. So therefore, I have the IX value. I know that E is always 200,000 MPa. That's the assumed value for structural steel. And I again get assumed value for structural steel, okay? So if you're doing structural steel, you can use that value, and assume that that's the value. If there's any other type of steel, you should don't blindly use 200,000 MPa. You should make sure that the E value of that particular steel, what it is. Now, so I've got all the variables that I need to calculate delta D, or the dead load deflection, and therefore I have 22.5 was what I calculated before WD. Of course, convert this to millimeters, so you're working the right units. So therefore, this makes no difference because kilonewtons per meter and newtons per millimeter is exactly the same thing. This all cancels out, that goes there. Oh, I've got millimeters. All my units work out perfectly, and now I will take my calculator and do the calculation. So if I don't check my units, I do this all the time. In other words, this cancels this. I'm sorry, that cancels that cancels that cancels that. That's there, and it goes here, and I have millimeters, and therefore that's the right units I want to get, and therefore I go through the trouble of, if I don't get this, I do this constantly, guys, even to this day. If I don't get the right units, don't bother calculating. You're doing it wrong. So I'm telling you right now, don't even bother taking out your calculator until you've checked your units. And I tell you, like, doing this has saved my tush a couple of times by making some serious mistakes. Okay. And unfortunately, in real life, there's no answer in the back of the book. You've got to make absolutely sure your calculations are correct. And this is one way to make sure that you're on the right track. And it's just good practice. That's all it is. Now, I get 12.2. Of course, the 0.2 is pretty insignificant. You know, everybody appreciates what 0.2 millimeters is. So I would sort of say like my dead load, my camber would be 12 millimeters. Understand? And if I wanted to camber this beam so that eventually when my dead loads get placed get supported by the beam, in theory, it should come out and be relatively straight as opposed to having a 12 millimeter sag over a 6 meter span. And that's what you're trying to do with the camber. Does anybody have any questions? Or is it all clear? We're all good? Yes.
It's clear, sir.
Go ahead,
I
guys.
see a different beam because when I was looking for on the beam table, I was looking mainly for um, the inertia, the amount of inertia. So that was my first criteria.
Oh, like, Nermin, you're absolutely right. They both, like, in other words, I tend to worry more about strength than serviceability in my choices. You understand? Because if I take my moment of inertia and my strength is not good enough, that could be more detrimental because, yeah, your beam is stiff, but it's like I'm trying to think of a situation where you look at your, like, for example, L over 360 starts being a fairly stiff beam. You understand? And a lot of times that's what can actually govern the choice. Okay. But for example, like, let's say I have a situation where deflection is not an issue and I want to keep it into L over 180. So that's a relatively, big deflection. And sometimes if I look at inertia, of course, you're supposed to be looking at both. So if you look at inertia and then all of a sudden your MR is less than your MF, that could have more serious consequences. Versus if I have the right strength in theory, and then all of a sudden I screw up on the inertia, the stiffness, well, what's going to happen is that this thing's going to start, vibrating or sagging and this and that. It's going to cause it may cause other issues, but at least it won't collapse on you. Okay. So, but all I'm saying is that the best thing is that I start with the MR, check the IX. If the IX is not strong enough, then I know I have to go up the table. I know that automatically my MR is going to be going up as well. So I'm only going to be that much safer in terms of strength. So that's what I like to do. Make sure my strength criteria is correct. And then after that, I check my serviceability, and many times the serviceability will actually force me to go and get even a higher MR. But if my serviceability, I can go down for my serviceability, I won't, because my MR is going to go down also. So I first worry about strength, and then I check my serviceability, and then I make sure both have been satisfied. Okay. So I suggest
So
that.
the basically there's no, as long as everything is like
Well,
below the MR below the more than the MF. There's no like right or wrong answer. There's just a better choice.
oh,
Like
the only wrong answer is whatever you choose causes a problem. Okay. So in other words, if you choose a beam that's got a stiffness less than what you need, it can cause you a problem. Okay. If you choose an MF less than what you need, that can cause you a problem. If you choose an MR that is 3 times your MF, that will never cause you a problem. It's only going to cost you more money. So is that a problem? Not to you, to your client. You understand? So there's, like, in other words, if you choose, I chose an IX of 572 times 10 to the 6, and I chose an MR of 582. Do I worry? No. Boy, I only need 272 and I got twice that. And I only need this. Oh, or put it this way. Okay. Nermin, your client's got a beam that he picked up at the scrapyard. Okay. Okay. Let's just put it this way. Okay. I'm going to stop. Well, let me just, okay. Okay, so like your client's got a beam. He went to the scrapyard, and guys, this is I was talking to a contractor the other day, and he was telling me the price of steel, how it's going through the roof. Okay, so for example, your client wants to save a few bucks. Instead of buying some, brand new steel, he goes to the scrapyard and he buys a beam that's, not rusted. In other words, it's in good condition. It's very, very usable. In other words, there's no rust or anything. And and well, I'm gonna come here. Okay, and all of a sudden, okay, so all of a sudden you come here, and he says, "Hey, I bought a 530 by 66." Right? That's what I have. Okay. You do your calculations and you know that a 410 by 46 is adequate. And he tells you, oh, I got a 530 by 36 that I bought from the scrapyard. Here's your MR value. Here's your IX value. Here's your VR value. Are you going to say no? You know what I mean? So, anything above this, it's going to satisfy your design requirements, and therefore they're all good choices. It's just that if you want to be competitive in the marketplace with against other consulting engineers, you have to make sure that you try to make the thing as close as possible as what is required. Otherwise, your client's going to say, "Hey, my structure cost me so much more than I had it designed by the other engineer. I'll never come back to you again." You understand? So that's the only problem. The only reason why people are looking for what is the lightest beam I can use is because they've got the guy, especially contractors that are building, constantly. They have a very good idea how much things are supposed to cost, and all of a sudden they say, this project cost me $6,000 more than when I did the other project with the other engineer. I kind of question. You might have over designed a few things, and that's ended up costing me a lot of money. So in the back of his head says, well, I'll go back to the other guy. He might charge me a little bit more for his consulting fees, but I will ultimately save it on the construction costs. You understand? So that's the only issue. So other than that, there's the bad choices is that if all of a sudden you're down here and you choose something in this area here, yeah, those are bad choices because your MR value is no good. You understand? Like all your MR values here, like any of these choices are bad because your MR value is not greater than your MF value. But in this case here, anything above here, if you choose that, there won't be any consequences. Okay, is that clear, Nerman?
Yeah, thank
Okay,
you.
so okay, I just thought I'm gonna basically close this and close this and oops, sorry. Okay, so where am I? What's happening? Stop sharing. Okay, so now today we're going to talk about the next element that is very important when you're designing anything. We're going to be talking about columns. Okay, so I'm going to okay, where is it? There we go. Okay, now guys, we'll talk about columns, and I want you to appreciate one thing here. Okay, is that okay? Let me start from here. Slideshow from beginning. Okay, now read what's on the screen yourselves. Doubly symmetric columns. Okay, and of course, uh, okay, so this is only this whole lecture and all of these formulas and all of these tables is only good for the thing, a shape that is symmetric about the x-axis and symmetric about the y-axis. Okay, so that means that if I decide to use a HSS, I don't care if it's rectangular, I don't care if it's square, and I don't care if it's round. And if I decide to use a wide flange, And I don't care if the white, I'm sorry, a white flange. I don't care if I use a white flange. Okay. As long as I have symmetry about the two axes, it has to be, in other words, it has to be symmetric about the two axes. I can use all these tables, I can use all these formulas, and it's only valid for double symmetric columns. If I want to use a C shape for a column for some reason, okay, or I want to use an angle to make my column, okay, then you cannot use these tables. There are more complicated formulas that you need to go to be able to use these shapes. And very rarely do we use these shapes for columns. Now, if ever I want to use angles, what I would do is I would weld another one here like this, and I would make it symmetric. And then if I want to use C's, I would weld another one here like this, and I would make, and then once I weld these together, then I can use this. As long as it's symmetric and as long as it meets another criteria that you see later on, you can use these formulas. So this is only for double symmetric shapes, okay? And you can actually build double symmetric shape, it would still work, not a problem. But make sure you have double symmetry. In other words, it's symmetric about the X and symmetric about the Y, okay? So I just want to stress that because some people don't, like, and I can tell you that when you want to design just a one steel angle as a column, the formulas become very, very involved. I won't say complicated, but very involved, okay? So keep that in mind. So this is very important. That's number one. Now, here is the equations, okay? Now, guys, I'm giving you this so that you guys, if ever you want to, well, first of all, I'm going to probably use this sometime in one of the labs, so I might as well explain it, okay? So this here is how you calculate the actual compression, okay? In other words, how much a shape can resist, okay? The flexural buckling of a double symmetric shape, okay? Again, okay? The factored axial compressive force, CR, okay? And of course, in steel, they still use the word CR instead of PR like they do in wood and they do in concrete, CR. For double symmetric shapes meeting the requirements of table 1, and we'll go look at table 1, okay? And you have to check to make sure it meets that requirement when we get down here, okay? Here's the equation, okay? So it's not that complicated, okay? This basically is simply the area multiplied by the strength of the steel, and of course phi is, and that's why we use a reduction factor for the material, 90%, and because of this phi, they call it factored axial compression, okay? And this accounts for the length of the column, okay? So in other words, what that does is that the longer the column becomes, the more likely it's going to buckle, therefore its strength is going to be going down significantly. So phi is 0.9. That doesn't change whether it's acting in compression, in bending, in tension. The resistance factor for the material for structural steel is always 0.9. In other words, when they actually produce steel, structural steel, the quality control that goes in there is fairly good, and you can rely up to 90% of the time that it's going to meet that resistance that you've assumed your Fy to be. That's why it's 0.9 as opposed to reinforcing steel, which is 0.85. A, of course, is your cross-sectional area. And this is the strength of your steel. And right now we're using, okay, the most common value that we find for shapes is 350 MPa, okay? Now, the n value here in this equation here, okay, there are two values for n. N is 0.13 for hot rolled, okay, fabricated structural sections. Okay, in other words, all the W shapes that you have out there, they're all hot rolled. They have to be hot rolled, otherwise you wouldn't even be able to roll them. And hollow structural sections manufactured in accordance with Class C. When we get into columns next week, I will tell you what a Class C means. A Class C means that they take a plate and they bend it and they make a hollow structural form out of it, okay? In other words, because of the bending, there's stresses, and therefore, so you're going to see when we talk about columns, not next week, the week after, because next week we're going to be talking about something else. Like there's going to be two classes of HSSs. One is a Class C, that means that it's shaped from a plate that is simply bent, and then the H, it means it's hot, it's been extruded, and therefore there's less stresses. So this, and of course, because this has less stresses, you can go up with the value of N, and you'll see in the tables when we look at the HSS class H, there are a little bit more resistance. So this is the value that goes here, okay, and there. Now, lambda is basically the strength of your steel divided by what they call the, well, they call this the, sorry, Fe is the, what is it called? I'm trying to remember off the top of my head. Fe is the Euler's buckling resistance, okay? And so, and of course, this is how you calculate Fe. In other words, if you notice, like you see here, KL over R is the slenderness of the column. And in this case, you square it, and then you take pi squared, and you multiply by E, and that gives you the Fe. So this is the Euler's buckling strength of your thing. And then once you've calculated the Fe value here, you simply take it in the Fy divided by that, you take it, and that gives you the lambda value. So the N value, 9 times out of 10, if not 10 times out of 10, if it's double symmetric, you'll be using 1.34. And the lambda is calculated based on these two formulas. One, you calculate the buckling resistance of the column, and then you calculate the lambda value. So that's the equations, okay? I'm not sure, like I'm not sure if I'm gonna do an example where I'm gonna apply I think I'm gonna do one example where I'm gonna go run through the equation, show you how to use it very quickly, and then we'll compare the values from the equation with the values in the tables, because there's and we'll see if we're getting the same values as in the tables. Okay, now, clear all drawing. Now, to go back to what we were saying here, okay, table 1. Table 1 is very similar to what we did when we decided a class 1 section, class 2 section, class 3 section. It's very similar to that, but this one is, of course, that was for bending. This is for pure axial compression. So therefore, the table is slightly different. Okay, and let me just clear this. So this here, you'll see that it looks very familiar. Okay, so here you go. Okay, in order for you to be able to use these tables, okay, and all that, you've got to make sure that these ratios are met. Okay, so for example, elements supported along one edge. Okay, so if I look at my shape here like this, this is my W shape, right? This is an element, and it's only supported along one edge. So that's why it's this element here that you look at. So in other words, it's BL over T. And when you take, in other words, this here is the T value. Half of B is the BEL value. In other words, this is simply you take your B value from your table and you divide it by 2, and that gives you that. If this ratio is less than 200 times this, divided by the square root of Fy, if this ratio is okay, you've met the criteria, and this is what they mean by elements. Okay, flanges, okay, here, flanges are eyes of T's and all that, channels, okay, so that's what this is. Legs of angles are elements that are supported along one edge, okay. Plate girders, but again, you can't use these equations for angles because it's not double symmetric, okay. Stems of T sections, again, you can't use these equations because T's are not symmetric, but in other words, this is just the table 1, like, so this way, when you look at the other formulas, they're going to tell you, well, if you're designing a T, you have to still meet these criteria. Now, flanges of hollow rectangular sections, okay? So in other words, if this is my, okay, and what they're saying here is that you take, that's why here, this would still be considered the flange, and therefore you take, again, this will become the BE value, you take your T, and so on, okay? Web supported on both sides. So for example, you'd have to check here for here, and then for this element here, you'd have to check this one here, okay? Now you'll see that when we get into columns, I think that I'm not sure, but in one of the spreadsheets that I'm going to be giving you, I put these two formulas in. So as soon as you put a choice, the spreadsheet will check it for you whether you meet the class one. And if you meet the class one, then you'll be able to design the columns with it. Okay. So I have this in the spreadsheet already. Okay. Now perforated cover plates. I don't know. Okay. And of course, for round sections, this is you take the diameter of your round section. This is HSS's, hollow structural uh, shapes, and divided by the thickness of the wall, and that's the criteria. So this is table one, okay? And like I said, you should always verify this to make sure that the member that you chose, or I should say the shape that you've chosen, meets these limits, okay? So that they don't prematurely buckle before the member is able to attain its full strength. That's what these things do. It's
Sure.
just to assure that there's going to be a global failure in your member and not what we call a local failure. Okay. And that's what happens when you start getting into class 3, class 4s, and so on, because these things become so thin, it's most likely going to be weak at one area, and that's going to govern the whole strength of the material. So that's table one. And like I
Sir,
said, yes.
I have a question. And I'm just trying to relate to wood. I know that the studs have each stud like has a weak axis and a strong axis here, because the shapes are symmetrical. There isn't any weak and
Yes,
so
there's weak axes and strong axes. Okay, in steel. Okay, in steel, as a matter of fact, this is where you're going to appreciate. Okay, you're going to look at the Rx value, you're going to look at the Ry value. In other words, the radius gyration about the x-axis is always going to be bigger than the radius gyration about the y-axis. And then when you do your slenderness ratio, that's the one that's going to govern. You always have a strong axis and a weak axis. The problem is, or not the problem, is that in wood, okay, in wood, this is what you have in wood. You have nice rectangular sections, you see? And the material is fairly weak. I'm talking about the the material. The resistance of the material is fairly weak. In other words, steel, you have 350 MPa. In wood, you have 9 MPa. You understand? To give you an appreciation. Now, what happens is that in steel, because it's very, very strong, okay, because it's very, very strong, what happens is that these plate elements, when they're in compression, they can fail locally. And therefore, by failing locally, what's going to happen is that as they add more strength, instead of you being able to take advantage of the whole cross section to give you resistance, this thing failed, the whole thing's going to
yeah,
collapse.
I see.
You
I
see, so
see.
so in steel, it's just to make sure that these plate elements aren't the ones that are going to govern the overall resistance of the member. In wood, not a problem. I know that it's always going to be the overall section that's going to give me my resistance. But in steel, you have to check if I'm going to rely on this whole area here. Okay, if I'm going to rely on this, let me just change color. If I'm going to rely, like in other words, see here, A, you see that? That means I am relying on this whole area here to give me my resistance. Okay, and that's assumed that the whole thing will eventually get to that yielding point. But all of a sudden, if this is too thin, this thing can buckle before my whole area will contribute to the resistance, and therefore the member is still going to fail.
Okay, got it. Thank you.
Okay, and that's why in steel you got to be. And as the steel gets stronger and stronger, and they can make these plates smaller and thinner, it becomes even more and more critical. As a matter of fact, have you guys ever seen metal studs?
Yeah, I've seen them. There's
You
so
see
thin.
metal studs, right?
Yeah,
Well,
yeah,
believe it or not, I design metal studs. But
for sure.
if you want to design with metal studs, you got to go to S136. That's the standard because the material is so thin that it's all the local weaknesses that control your design. And that's why it's a completely different animal and a completely different standard and a completely different formulas. Very similar to these, but very, very more complicated. You understand? So you can design. I design steel walls and I design, like so. But because these things are so thin, like it's just sheet metal that's been bent into these shapes. I mean, these things become very, 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 very local weaknesses that control the design. So instead of me relying on this whole cross section here, I'm just relying that when one of these plate elements will actually fail. That's what I'm doing. Okay. And so keep that in mind. As soon as you start getting into a class 4, you got to go to S136 because that's the standard that has all the equations for that thinness of material. Okay. So that's table 1. And then after that, I think I showed you this. Oh yeah, this here. This is just to remind you what that here, because remember you have this K value here, because the standard, this here, as I told you, okay, KL over R. Oh, I shouldn't have taken this one. KL over R, whether no matter what material, this is always called the slenderness ratio. That's the slenderness ratio. And then K, of course, is the effective length factor, okay? And so I think I showed you this. This is like, remember I showed you one for wood, okay? Now there's one for steel. Now they're very, very similar, okay? Now here, two things you have to keep in mind. One is this shows you the end condition of how your column is fixed to the structure, okay? So what does this mean? That means that the column is fixed there and fixed there. Okay. In other words, you've got to make sure that there's no rotation of this point. There's no rotation of the point. Then what happens is that this becomes the possible deformation of the column. And therefore, in theory, here's a point of inflection. Here's a point of inflection here. And therefore, in theory, this is the length that's going to buckle. In theory, and that's why we can actually reduce the length here of the column to theoretically only half its length for buckling. Okay. The same thing happens here. Here it's fixed here and it's pinned there. So therefore, if you look at the point of inflection here, somewhere around here, and then if you go all the way up, you're looking at 70% that will deform and possibly buckle. And of course, the most typical one that we use, and especially in steel, because creating these conditions in steel is very difficult. It takes a lot of welding, a lot of plates and all that. So we tend to always pin, like use pin connections. These are very easy to create in steel. And therefore now the whole length of the column is what's going to affect the possibility of buckling, and therefore the K value is 1. And then like again, when the whole thing can move out of plane, it becomes very critical. In other words, the length becomes twice its actual length, and these become, well, not this one here, this is fixed, but when it's fixed pinned, you'll see that the length becomes twice the actual length, and this can really hurt you. So if you don't brace your structure and the structure can sway out of place, the length of the column becomes drastically longer, and that's what's going to actually collapse on you. Okay, so here, these are, like I said, these are just graphical representations of how you're preventing the movement at the reaction area, at the connections. Okay, and therefore this means that I allow no translation and no movement X, no movement Y, and on top of that, I don't allow this thing to actually rotate about that point. Okay, so this means, that's what we mean by fixed, that there's no degrees of freedom. You can't rotate on me, you can't move this way, and you can't move that way. Okay, and the difference is that here, I can't move this way, I cannot move this way, but I can allow you to rotate about that point. So therefore, there's no moment, and that's what this is. Okay, and of course, this means that it's free to move out of it. This is just another. So these are just graphical representations, and that's why you have to understand, what do we mean by fixed? And what I mean by fixed is that there's absolutely nothing that can displace. No X, no Y, and no rotation. What do we mean by pinned? Well, X and Y are fixed, but it can rotate. And what do we mean by a roller? Well, one direction is fixed and it can be free to move, okay? And it's free to rotate. So that's what we mean by those three conditions. So this, like I said, and the other thing I want you to note here, guys, okay? I want you to note one thing, okay? Where is the load applied? This is valid when the loads are being applied at the extremities of your member, okay? I tell you right now. So also look at where the load is applied, okay? I got involved in a file where we had columns here like this, okay? And on the columns, there were brackets, okay? And the brackets were supporting these pallets, okay? And we're supporting these pallets like this. And because the loads were applied through the length of the member, I recalculated the K value for this, okay? and it's very complicated. Well, not complicated. You got to know what you're doing as an engineer. I recalculated the K value, and the guy, the other engineer that was working for whoever, he said that the K value was equal to 1.0, and I said no, the K value in this case was equal to 0.35, which drastically reduced, okay, the effects of the buckling, and therefore it drastically increased the resistance of the column. And of course, like we didn't have to go and modify anything. Okay, so that's that. So keep in mind that that's when the loads are being applied at the extremities. Okay, just for your information. Okay, so that's the K value. Okay, now I think I showed you this in concrete. Okay, and what I liked about this picture is that it gives you a very good appreciation. Like here, the lengths are all the same. L is the same. Okay. Here, the only thing that changes, the member is the same. In other words, they use the same cross section here, the same member. Okay. So the member is the same. The lengths are the same. The only thing that's different is how is the end condition of these columns. Okay. And what I like about this picture is that it gives you a real appreciation of, for example, when I have a fixed, look at the load that this column can carry, as opposed to when we have it's fixed and it's free to translate. Look at that. Okay. Isn't that amazing? Okay. That's like, in other words, when the K value goes to 2.0, and here the K value is 0.5. Okay. Now here, when you can see that when it's fixed and pinned, where the K value theoretically is 0.7, okay, it can still hold a substantial amount of load, but yet it's less than when it's fixed. And of course, when it's pinned, okay, in theory, approximately, okay, this approximately will hold a quarter of what it's holding here, approximately, okay? So that's what I like about this, that you can see that just keeping everything the same, the length of your compression member, keeping the same cross-sectional area, the same material and everything else, how just the end conditions will affect the resistance of a member that's in compression, okay? And when I saw this the first time, I thought this was, for me, it was very, very clear what they're trying to show you here, but you can also get an appreciation. So they actually fixed this, they fixed that, and here they pinned that, and they fixed that, and here it was fixed there, and it was free to, you see, all they did is they made it, like, put it like on a roller here, so it was free to translate at a plane. And here it's just pinned. In other words, the thing can just rotate and not have any resistance to rotation. And it gives you a very, very good appreciation of how it can drastically improve or reduce your load carrying capacity just on how it's constructed at the ends of the columns. Okay, so any questions here? Is it clear? Okay, now maximum slenderness ratio. Now in wood, we saw that we had a KL over R, or K, and would we say KL over D or KL over B, because we're talking about those two dimensions, was maximum 50. Well, in steel, it's a little bit more. For a compression, for a membrane compression, okay, whether it's like a column, somewhere in a truss, whatever's in compression, it could be a strut, it could be a web member, and whatever's in compression, the slenderness ratio, KL over R, cannot exceed 200. Okay, so in other words, if you happen to go over 200, well, the reason why they put it 200, you'll get an appreciation here. Okay, so this is, for example, the yield strength. Okay, and this is the slenderness ratio, KL over R. You can see that the resistance, or the amount of stress that you can apply to the column, will, like, at one point will start becoming drastically reduced to the point where it's almost ineffective. Okay, so therefore that's how they ended up saying, well, let's limit it to 200. So therefore after that, it makes no more sense. Okay, so that's why they have this ratio here, and it's basically, in other words, this here is like, if I wanted to put it in approximately. I'm just going to try to put it in approximately. In other words, this is where KL over R is 0. Okay, and that's where you can get the maximum. In other words, if I have a very stubby piece of steel here, well, it's just gonna yield. It's not gonna buckle. Okay, so a very stubby piece of steel that's being loaded with a very short thing, wow, it's just gonna buckle. It's gonna yield on me. It won't buckle before it yields. And then as the member becomes longer and longer and longer, and in other words, I shouldn't say the member becomes longer, as the slenderness ratio, because the slenderness ratio has got nothing to do with length, is that KL over the radius of gyration here. Okay, as the slenderness ratio becomes longer and longer, at one point they say, let's just limit this to 200 because it's going to be so weak that it's not even worth going beyond that point. Okay, so that's what they're trying to show you here. So when you're doing your calculations, if ever you're, for example, first thing we're going to check, we're going to set the slenderness ratio of whatever we chose. If it's less than 200, we'll keep going. If it's greater than 200, well, we will stop there. We'll go back and find something that's got a slenderness ratio less than 200. That's what that's all about. Okay, so now let's put all this good stuff. How are we doing time-wise, guys? Pretty good or
It's good. It's
good?
almost 9.
Almost 9? Oh, we have lots of time. We have until, okay. I have a W250 by 73 section. Okay, the steel, like I said, don't look at the steel. The steel just tells you what the Fy value is here. In this case here, the Fy value is 350. To be used as a pedestal, the height of the column is 1,100 millimeters. So that's not very long, okay? And it says determine the compressive resistance. Okay, the effective length factor here, we're going to assume that the column is pinned, okay, and therefore K is equal to 1. And like most columns, we'll always consider them to be pinned because the base plate does not fix the column. The connection from the beam to the column does not fix the column. Therefore, we'll always assume it to be pinned. So we'll always assume K is equal to 1.0. Now, what you need to do, of course, okay, you go, I think I sent this table. I believe this was in lecture number 2. You guys already have this table. So I have a W250 by 73. I'm just going to write it down, 250 by 73. I go to the table to make sure that I get the, I come here and I'm looking for a W250 by 73. So I'm going to go down W250 by 73. I come here to make sure I have what they call, I meet the requirements of table number 1. So I'm looking for a W250 by 73. So I'm going down, hold on, W310, W250 by 73. So here I am, I'm here, okay? But this is the sectional properties on the next page. Like I said, these are like side by side in the handbook. So, but if I want to know where I am on the other page, I simply go look for the 73. So here I have the value of B, I have the value of T, I have the value of W, and I have the value of H. H is simply the overall height minus 2T. So if ever you guys want to check the values in this table, you take 254, subtract 2 times 14, and that should be your H. So this is check for that BE over, like the BEL over T value here. So I take my B value divided by 2. T is the thickness of the flange, you see it here. And of course, W is for the web. We also have to check the web, and this is the height of the web, and therefore it's H over this has to be less than the value that we have in table number 1. And BEL, which is B over 2 divided by this, has to be less than the value in the table. So that's why I come to these tables here, just to make sure that I am, so, and on top of that, I get my area. I forgot, I get my area, I get my radius of gyration around Rx, Ry. I forgot about that, so I apologize. I'll go back just to make sure that we see where those are. Okay, so if I go back a page, so this, of course, for columns, I need, okay, so here is the areas of all the shapes. Okay, so therefore there's the area right there. I need that to calculate the resistance of the column. And this is where I get the Rx value. And I get the Ry value. Okay, and remember, if you take if you take the moment of inertia here, Ix, okay, if you take the square root of Ix over A, that will give you the value of Rx. And if I take the square root of Iy over A, that will give you the Ry value. And that's why the raised iteration about, because Yy is always weaker. In other words, it's not as strong. The Y value here, 38 as opposed to 113, is always a smaller. That's why we call this the weaker axis, because the raised iteration is bigger, and because the raised iteration goes into the denominator, it gives you a bigger slenderness ratio, and that's why it becomes a weaker plane. Okay, so that's where we get those values from. I apologize about that. And like I said, the total flange weight, okay, is 254. H is the values of D minus 2T. And of course, if you go to table 1, check for local buckling requirements are met for table 1. And of course, if we go back to table 1, well, this is for the flanges of I's, T's, and channels. So therefore, it would be BEL, which is half of B over the thickness of the flange, 200 divided by the square root of Fy. And for the web, it would be H over T. And of course, this becomes 600 divided by D. So therefore, this becomes a bigger ratio here. But because this thing is supported along the two edges, it allows you to, use this ratio here. That's where we get those two formulas. So I check one. So in other words, like I said, 225 divided by 8.6. Okay, it meets for the web. And then for the column, I take half of the B, which is the BEL. In other words, in other words, what this is just that part that sticks out from where it's being supported. Okay, so that's why they want you to take only half, okay? And that's why you take half of the B. So it's B over 2 will give you the, what they call the BEL, okay? The B of the element, that's why they put EL here. And of course, T is always represents the thickness of the flange. And this here is 8.9, less than 10.7. That's okay. In this case here, you got 26.2, less than 35.5. Oh, okay. So I meet the requirements of table number 1. That means I'm allowed to use that formula. Okay.
Yes, sir.
Yes.
And what if you don't meet their requirements?
Then don't use these formulas. Change shape.
But in the test, it would obviously meet the criteria, right? Or you want us to change?
What I'm saying is that don't just blindly take a shape, whatever. Like if you see how many shapes there are, right?
Yeah.
You can appreciate that. So you just don't blindly take a shape and assume that it's going to meet these requirements. You check them.
Okay.
And if they don't meet, choose something else. Or if you want to use that shape, go find the other formulas in the handbook that can treat this particular case. In other words, you're probably going to end up having a local failure, and therefore you're going to have to reduce how much that thing can actually carry.
Okay. Thank you.
It's like most shapes will meet this, so you won't necessarily have a problem, but you should always check this to make sure that you are allowed to use either the formulas or even the tables. Okay. Now, the nice thing about using there's one table you won't have to worry about it, because I'm sure that table has already incorporated these formulas, but there's another table where it hasn't incorporated these formulas, and therefore you have to check if you want to use that particular table. Okay, so even certain tables have this already built into them because they limit, you understand, or I'm just saying that this has to be verified, and just don't blindly assume that it does. I mean, and if it doesn't, it can really hurt you. It can really hurt you. So now, okay, so here we go. I'm going to do this only once in this course, use the formula so you guys can know how to use the formula if ever you want to use the formula. But again, you use the formula only if you've verified that it meets the requirements of table number 1, okay? So the slenderness element of the web is less than the values of table number 1. Therefore, the cross-sectional area will not fail by local buckling, and its capacity as a column can be predicted using this equation, okay? And that's what that table does. It kind of assures you that you're going to get an overall failure and not a local failure. So now, phi, of course, okay, we check the slenderness ratio. That is KLRX, okay? And KLRY. Now, it's always the higher slenderness ratio that will govern your resistance. In other words, because it goes into the denominator, okay, it drastically reduces, the value. And therefore, now here it's less than 200, not a problem. Here is still less than 200, not a problem. But out of these two, I'm going to check the resistance with respect to the y-axis. In other words, if this thing's going to buckle, it's going to buckle about the y-axis and not. In other words, when I go to the site and I see this column has failed, most likely it will be distorted about the y in the y direction than in the x direction. That's what this means. Okay. So that's the one that I'm going to be using in my calculations. Now, this is, like I said, this is the buckling resistance of the. So this is Euler's buckling resistance. Okay, this is mathematician. Some people like to use the word Euler. I like to use Euler, whatever, EULER. He's a mathematician. He came up with this formula. Okay. And basically it's pi, don't forget to square the pi multiplied by the modulo of elasticity. And then this is your slenderness ratio, and don't forget to square it. Okay, very important. So this is the ultimate buckling resistance of this column. Okay, so that's the FE value. Now, if you remember, lambda was, okay, so lambda was equal to Fy divided by Fe. And of course, here I told you it's 350, and therefore I can use the 350. If it was the American steel, I would be using 345. That's the only difference. And then, of course, and therefore this becomes the value of lambda. Now that gives me the value of lambda. And if you remember from the first slide, I don't think you did, but there's the n value. There's two n values, 1.34 and 2.2 something. Of course, we are in the rolled sections. Okay, so therefore the n value is 1.34, and the a value we got straight from the table, right? And therefore now I've got my n, I have my lambda, I have my a, I know my Fy, and I know, of course, my phi, the resistance factor for structural steel, is 0.9. So therefore, 0.9 times my A times that. And guys, this here, be careful. I hope you know how you do this in your calculator. Understand? Like, in other words, don't forget, it's the inverse of, understand, of this value here. It's a -1. And this, of course, is squared here. So, and if you do this correctly, and of course you multiply by 10 to the -3, I should have put this as a superscript, but I forgot to do
Sorry.
that. Yes.
When you use the n, how would you like? I've never worked in a factory, so I don't know which n, like which how they did it, or you explained. So
If you're allowed to use this equation, there's
yeah,
only two values of n.
yeah, I know.
It's either 1.34
Yeah, but
or
you said one it's when it's hot rolled, and the other one is for
no, like one is like any section that you buy, any wide flange section, okay, they're rolled hot.
oh, okay.
They have to be hot, otherwise you can't roll them. You won't be able to work the steel. Okay, so any section you buy is rolled hot. Okay, so all the W sections, all the T sections, I'm not the T, but the angles, the channels, they're all rolled hot. Okay, now, and then as far as the HSSs go, there's two ways of making HSS. One is you take a plate and you bend it, and it's called, okay, cold form. In other words, the plate is cold and the machines actually just bend it, and then it gets welded along the seam. That's where you use 1.34. Then you have HSSs that actually get extruded, just like they're hot and they get extruded. And therefore, because they're hot, there's less stresses. You're allowed using a slightly higher value of N. So the only time that you use the other N is when it's for a class H HSS. And you can get them, but I do not recommend that you specify that because they're rare. They're not as available as like the class C. And on top of that, when we get to columns, I'm going to recommend that you just take the American steel because they're the weakest and the most available. Okay. So that's how you know what N to use. Like, it's very simple. First of all, the other one is just for HSSs and welded wide flange sections. Are we using welded wide flange here? No. Are we using a HSS? No. So therefore I know I got to use 1.34. I can go back to the first slide and read it again, but when you review the slides, you can go back and read again where N is used. And then of course, like if you're not sure, you only have two. If you're not sure, just use the lower one. You're going to be safe because if you happen to be entitled to use a higher one, you're just going to calculate a smaller, a lower resistance, but it's actually going to be higher than what it actually is. So don't worry about that. When in doubt, always use the one that's going to give you the least resistance. I can tell you right now that if I use the other one in here, the CR value will be greater than this. That's all. Okay, so if you're in doubt, Omar, take the smaller one. That easier to remember?
Yeah, easy.
Okay. Now, here I end up getting a CR value of 2,881 kilonewtons. So that's using the equations, okay? Now, of course, I did this once because I wanted to show you how to apply the equations. In other words, you always calculate the slenderness ratio. Now I'm going to show you two other ways of doing it, okay? And of course, we're going to be using these methods whenever we're going to be calculating our columns, but I wanted you to at least have one example where I use the equation. And now, using tables to determine CR, okay? Now, using table 4.4, this is a nice little table, okay? This is a nice little table to obtain the values of the unit factor compression. Okay, so what the table does is, so that you guys can appreciate, that you go in the table and it gives you this value here. What the value that you're reading out of the table, you're reading the value of CR over A. That's what the table gives you. In other words, it gives you something in MPa. Okay. So since I already have that value, all I got to do is multiply this by the area of my shape. And of course, times 10 to the minus 3. And my CR value is given to me right away. Okay. So what this table does is that it already takes into account the N value. It already takes into account the slenderness, the lambda, and everything else for you. So you don't have to calculate the, okay. So that's what's nice about this table here. So here's the table, and like I sent you this table. You guys have this in your, okay. So here's a table. Okay, now, guys, with any tables, you always very carefully make sure that, okay, this is for when the N is equal to 1.34. In other words, okay, if you're using a wide flange section, you're there. If you're using a class C HSS, you're there. Everything is good, so don't worry about it. Now, okay, so the wide flange section and sections, there's another table if you want to take care of these two. So if you take this one and you have a class HSS, you're only going to be safer. Don't worry about it, okay? So what they've done here is they've taken the KL over R, in other words, the slenderness ratio. You go down until you hit your slenderness of 17. You go across, okay, until you hit your strength of steel. And you'll notice that they have one at 345, and that's for the American steel, the A922, okay? So I'm telling you here it's 350. So you see there's a slight difference between the American steel and the Canadian steel. We used to produce steel that was just slightly stronger than the Americans because they produce it at 50 KSI. That's their nice round number for them. So now I've got my CR over A value. Okay, so I can come straight here, take this value here of 311 MPa. So I got CR over A of 311 MPa. And now all I got to do is multiply that by the cross-sectional area. Okay. So in other words, I take that and then of course multiply by 10 to the minus 3. And I get 2,886. Okay. And there you go. But with the calculations, we got 2,881, and with this table we end up getting 2,886. Now, it could be a question of rounding off, but guys, trust me, it's not 5 kilonewtons that's going to be making a difference here. Okay, so that tells me that this table is relatively good. Okay, and therefore I can use it with a certain level of confidence because I've checked it by using the formulas. So this answer is as accurate as 2,881 kilonewtons. So that's one table that you can use. But then again, you're only allowed using this table if you verified that you meet the requirements of table number 1. Okay. Now, using the W columns. Okay. Now here, the W columns. Okay, so this is another table that I also sent you these. Okay, here what's nice about this is that they give you the effective length KL, but this is always the y-axis that governs. This is always the y-axis that will govern your choice. In other words, this is always KL, and it's always the RY or the KL of the y-axis that governs the length. So for example, if I happen to have and here what you do is you take the shape we had. What was it? Do anybody remember what shape we had? It was a W. Does anybody remember the shape? I should have written down the shape. A W200 by 73. Okay, so we had a W200 by 73. So I just go look for my shape. W200 by 73.
It was a 250, sir.
Sorry?
It was 250 by 73.
250 by 73. Thank you. Appreciate it. 250 by 73. So therefore I go here. Oh, here's a 250. Here's a 73. All I need to go now is find the length. Okay, so here, for example, I don't have 1100. I have 1250. As long as the length is longer than what I actually have, I can come and take the value straight out of the table. Okay, so here I have the CR value in kilonewtons is 2,830 MPa. I'm sorry, kilonewtons, and that's how I use this table. And that's always assuming that it's the weaker axis that will govern. And I'll show you how you can use the tables when it's the strong axis that will govern. I'll show you an example on how to do that. So that's this table here. So this table, what's nice about it, once I know the shape, once I know that the RY value is the one that governs the length, once I know the length of my column, I can get the CR value straight from the table, okay? And down here, there are other things that are all related to these sections, okay? And I'll show you how to use this RX, RY ratio here, and that's what you need to do for certain situations and so on, okay? So that's it, and therefore by using this table, straight from the table, I get a 2,880 kilonewtons, which is very close to what we had from what we calculated with the formulas, what we calculated from the other table. So therefore, these tables seem to give you the right, values for what you want to look for in the tables. And that's what I do. I like to use the formulas to check if the values in the tables correspond to what I've done in my formula. And if it does, well, then I feel comfortable using the table. That's another reason why it's good to know how to do things with the formulas. So this was, like I said, one was with the equation, one was using table 4.4, whereby I just know the KL over R thing, and therefore I can go get the CRA value multiplied by the area, blah, 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 and I get the CR value. And then here, if I know the shape, okay, so in other words, here I knew the shape, I knew the length, I was able to right away get the value of CR from that table. Now, what I'm doing here is I just want to show you what happens to the CR value when I go from 1,100 and I make it 10 times longer, okay, to show you how that drastically reduces the resistance, okay? So recalculate the compressive strength CR for the height of 11,000 instead of 1,100, okay, just to show you how length can drastically affect the CR value. Okay, so now the slenderness ratio for the RX is 100, still less than 200, not a problem. RY is 170, getting close to 200, and therefore it's starting to really be down there. If you remember that graph I showed you, how the slenderness affects the resistance, okay, so it's starting to get really low, okay. Now, I'm going to use this table here. So I go to the table with 170. I'm going to go to this table here. And now, of course, I have 50, 100, 150, 170. So I'm here. I'm at 170. And what I like about this table is 170. I go across. And therefore, there's my, 56.8. There's the value of CR over A, 56.8. Okay. So I take that value from the table, and of course, I've already checked that it meets the requirements of table number 1. So I can simply, okay, 56.8. Now, of course, I take the same cross-sectional area that I had before, 9,280, and I end up getting 527 kilonewtons. So I went from 2,880 kilonewtons down to 527 kilonewtons. So it substantially reduced how much resistance this column has. The fact that it is, fairly long compared to, it's 10 times longer than the first one. So, and then of course I can do the same thing with this one here. I'm going to go and look for the KL over R of 170 in this table here, and I'll get the value right away. So I have the same table here, 1100. Okay, so where are we? We're at 1100 here by 73, and there you go. And this was the W250 by 73, and then of course this one I get is 525. Wow. And then this also gives you an appreciation, like how drastically the length affects the resistance. You see how it starts dropping significantly. You know, at the beginning it's very small because, you know, like and then it really slopes down quite a bit. You understand? So I have 525, and therefore I have 525. This one gave me 527. This one gives me 525. They're in the same ballpark. They're both correct. So that's number two. Now here I'm going to show you. Okay, what happens when a column is laterally braced, okay, and the L values aren't the same with respect to the X and the Y, okay? And therefore, and I'll show you how you still use the tables and modify the tables to go and get your answer, okay? So here, determine the factor compressive resistance CR for the column shown in the figure below. Okay, the column is braced at mid-height to prevent movements along the X direction only, okay? So guys, this is something I want you guys to visualize. Okay, this is something I want you to visualize, is that right now, I'm putting a brace here. This is the brace here, okay? So the brace is holding here, and it's holding the column there, okay? So what's happening here is that the y-axis is prevented from moving, okay? So what I'm bracing is the y-axis, not the x-axis, okay? And the x-axis, this is where the x-axis is. In other words, if I look at it in plan view here, well, that's the x-axis. The x-axis is completely to move from here all the way down to here. So for the x-axis, this becomes my L value for the x-axis, and for the y-axis, this becomes my L value, because y can only move from here to here and from there to there, and the x can still move from here to here. And that's something that you guys are going to have to look at, and at one point you're going to get that aha moment, and you're going to start appreciating when I'm bracing something, which of the two sides am I bracing? And it's kind of a little confusing because people say, well, if I'm bracing along the x-axis, why is it the y that is, because it is the y that is prevented from moving out of its plane, and therefore you are bracing the y-axis. If I would have a brace here also in this direction here, then I would be bracing also the x-axis. Then I would, but in this case here, this brace will only be bracing the y-axis. Like if you look at the projects, we have our columns on the exterior, okay? And we'll do this when we do the exterior columns. We have the girts in between. Well, those girts are going to be bracing the y-axis, but they will not be bracing the x-axis. So therefore, it will affect the length of the y-axis, not the x-axis. And we'll be looking at that when we design the exterior columns for the project. So this is, okay, so this is something you should keep in mind. Now,
So I'm sorry. So it's preventing the movement in the y-axis?
it's preventing, like, look at it and ask yourself, I have a brace here. Okay, let me just, I have a brace here, like here. This is the brace. You see where the brace is? Okay, the brace is attached to the wall here. Okay, and it's attached to the column there, right?
So it's attached to the web mainly.
It's attached to the web, okay? So it's attached to the web, right? Like it's attached right here at the web, okay? Now, is which axis is going to be prevented from moving because it's being braced? Is it the x-axis that's going to prevent it from moving, or is it going to be the y-axis that's going to be prevented from moving?
Okay, but the y is already, because it's pinned a column, so it's already prevent it from moving, right? Or I'm
No, what
I'm
I'm trying
sorry.
to make, okay, no brace. There's no brace here whatsoever. What's prevented from moving?
The why?
Neither one. In other words, the length for the y-axis is the same length as the length for the x-axis. If when there's no brace, in other words, it's going to be KL over Rx and KL over Ry. And because there's nothing preventing it, you understand? But now if I decide to brace this, okay, if I decide to brace it here, I'm preventing the y-axis from moving out of its plane, out of its position. And therefore,
Okay.
so the y-axis becomes half of the x.
Okay. Okay. Yeah, I got it now. Yes.
You got it now, okay? And that's what you have to start seeing, understand? So in other words, like when this column wants to buckle about the x-axis, well, it's going to, there's nothing to prevent it from buckling. Therefore, the Lx value goes from there to there. Okay, like, or like if I try to draw this like this, okay, this is the column here, like this, okay? And when I put a load here, well, when this thing wants to buckle, it's going to buckle. This is going to be the length that it has to be able to buckle about. And therefore, this becomes the Lx value, the whole length. But with, as far as the y goes, well, it's braced there. And therefore, this becomes
Half of the
exactly half the length. And
like
if I would have two of them, then
it's gonna buffer like okay. Okay, I got it.
exactly. In other words, it can still it can still govern. You understand? It can still govern, but at least you know that it's got half the length that's gonna buckle under. Okay.
As if like I divided the column into two. Like the brace, it's acting like as if it's like a flange, and so it's
The brace,
buckling it.
the brace is telling the column, I'm going to hold you here, but I'm only holding you in one direction.
Okay.
And
Which
the
is the
direction
y.
that you have to see is the y. It's the y-axis that is not moving out of its plane. The x can still be free to go any way it wants.
Okay.
And therefore, so in other words, here the Lx value becomes 4,600, but the Ly value is half of that. It's 4,600 divided by 2. Okay. Now, here I put in the middle just to make it simple. But if the brace happens to be here, then you take this as being the Ly value. You understand? Whatever it is, you understand? You take the longest length that the brace is. Okay. Now, if I use a W shape, okay, okay. Now, the cross-sectional properties of a W200 by 46. Okay, so here we go. Did I tell you what determine the cross-section? Oh yeah, here I tell you what the size of the column is a W200 by 46. Okay, that's where I get the shape. I forgot. So if I come here, okay, if I come to the W shapes, right? I'm sorry, I forgot. What's the one that I want? W200 by 46. I should write this down. 200 by 46. I would come to the shape tables. Okay, you come to the shape tables and 200 by 46. So let me go 200 by 46. So here we go. So here's where I go get the cross-sectional area. This is where I get the radius of gyration, Rx. This is where I go get the Ry value. And of course, I should also check the, the table 1 requirements. And of course, on the next page, I get the B value, I get the T value, I get the W value, and I get the D minus 2T value. So this is where I get all both the sectional properties and the cross-sectional dimensions and so on. So that's where I get it from this table here. So therefore I get the A value, I get the Rx value, I get the Ry value. Of course, the H is a D minus the 2T value and then I check, okay? Again, we'll go back to this table just so that you understand what we're doing. We're going back. So this is for the flange and this is for the web. Okay, so the flange is based on this ratio here. And of course, you take half the flange width, B, to get your BEL. And here you take, this is for the web, okay? Because web supported on both, okay? So that's where you get the two ratios or the two criteria that have to be So here we go. So we have H over W, 180 over 72. That's 25.1 over the ratio of 650 divided by the square root of 350. And therefore, I get 335. That's good. And then for the second one, I take half of B, which is BEL, divided by T. I end up getting 9.2, and that's less than 10.7. So far, so good. I meet the criteria of table number one. I can either use that formula or I can use the tables, okay? Now, therefore, we can use table 4.4. If you don't do this check, don't use table 4.4. You can use the other table because that table has already got this thing built into it, but don't use table 4.4. And don't use the formula because you're not sure. So now the slenderness ratios, here we go. Now, KL over Rx, and of course, the length with respect to the x-axis is 4,600 because there's no braces preventing the x-axis from moving. And the KL over Ry is only half the length of the column because it's the y-axis is prevented from moving. And therefore, this is the one that governs. So in other words, in this case here, it's most likely going to deform and buckle about the x-axis as opposed to the y-axis. The y-axis is laterally supported at the mid-height. So therefore, this is the one that governs my design. Now, I know that the KL over R is 52. Therefore, I go to table 4.4. And of course, table 4.4, I know that this is good for what I have. In other words, N is 1.36. In other rolled sections, I can use this table. I've checked it. It meets the requirements of table number one. And therefore, I just go up and look for 52. Here's 52. Here's 52. And I don't know, did I say that our strength of steel was 350 in this case? Oh, 345, 350. And therefore, I have a CR over A value of 249 MPa. Okay. And of course, now just so that you guys can appreciate, okay? Let me go up one more. Sorry, I gotta do this. Okay. If you look here, okay? Does anybody know what 350 times 0.9 is? You see here, 315. This is 350 times 0.9. In other words, this is the factored resistance. So up to this point here, that means that when you have a very low KL over R ratio, the whole section will yield. The steel will yield before the buckling or the slenderness will affect the resistance. And then after that, it starts getting affected. And of course, it starts dropping as the KL value becomes higher and higher. And therefore, it's no longer just the strength of the steel that's going to govern the strength. It's going to be the slenderness. And that's what I get from this table here. So I got the value of 249 MPa and I got the area from the other table. So there I can simply do the calculation. And of course, because this is newtons per millimeter squared and this is millimeter squared, I end in newtons. Therefore, I have to multiply by 10 to the minus 3. And this column can hold 1,459 kilonewtons, which is pretty good. I mean, it's that means that this thing can hold 1,459,000 quarter pounders. If you want to realize what it can actually hold up, because a quarter pounder is about 1 Newton. So it's 1 million, almost 1.5 million quarter pound McDonald's hamburgers can sit on this column. Now, if I want to use a W shape, this W shape, the problem with that is that it's only good when the RY value governs. In this case here, it's the RX value that governs. Therefore, you have to manipulate the value in the table. And this is how you manipulate the value in the table, okay? RY is, but RX is 273. So you have to find an equivalent RX for the RY value. And that's what you have to do, find an equivalent. So the equivalent KLY value here, you take the KLX value that you have and you divide it by the RX divided by the RY value. In other words, we have the RX value, and this is how you find an equivalent KL for the table based on the LX value, because the table is all based on the fact that both are unbraced, and therefore it's always, and therefore, so now instead of me going to the table with, like for example, in table number 4.4, I went there with this ratio here, K of 52, but in the table of 4 point, I'm sorry, the other table, the W, instead of taking an L value of 4,600, okay, because the Rx value is much stronger than the RY value, and this is how you find an equivalent value for that table. Okay, I go down and I'd only have to go find a length of 2,647. So if you want to use the W column, this is how you have to use it when it's the Rx value that governs the resistance. You have to find an equivalent KL value here. I know it's a little complicated, but this is how you can still use the table. And if you don't use this table, just use table 4.4, 4-4. So now I'm looking for something that's at least 2,674 millimeters long. And of course, my shape was a W200 by 40, whatever it was. We had, so we had what, a W200 by 46? Is that what it was? That's right. So here, if I come to the table, now that I've got an equivalent KL value, okay. See, it says it here. This is the effective length, KL, with respect to the least radius gyration. And here, if you want, in this table, they already give you that ratio of Rx. So you can pull that right here. You don't have to do it manually. It's not a quick calculation if you already calculate. But if you ever need to find the Rx over Ry value, okay, and then you can get that value right now. And therefore, I come here. Of course, I don't have 2,600. And I come across, and there is my CR value if I want to use this table. So that's how you use this table. Okay, and we can do another example if it's, I know it's a little confusing sometimes, but so for KL is equal to 2,500, CR is 140, okay, and then for 2,000, it's 141, and if you want, you can interpolate between the two values, or you can simply go and take the higher one and simply say it's down to 1,000. Instead of using this value here, you can take you can use the smaller, or if you want, you can interpolate between the two values. It's up to you. So that's how you, when the Lx value governs the length, okay, in other words, it's the Rx value that governs the design, you have to find an equivalent Rx length, and that's what you do. You take the actual length of Lx, which was 4,600, and you just simply divide it by this ratio here, Rx over Ry, and you saw that this is what you had at the bottom of the table, 1.72, and that gives you the equivalent KL value for that table, and therefore you can take this length to go find your CR value. That's what it means. So now, determine the lightest size. How are we doing? Am I taking away? Oh, I think we have just enough time. Okay. Now, determine the lightest size square HSS. Okay. Okay. Class C column for the following conditions. Okay. So, the dead load is 1.2 kPa. The snow load is 4.8 kPa. Okay. The tributary area is 90 square meters. So in other words, this thing is supporting a surface area of 90 square meters. And guys, whenever it comes to columns, it's very simple to calculate tributary areas. I mean, if I have a square HSS there, and 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 I have another one there, and so on, okay? So just like what you did for whatchamacallit, like in this case here, half the load here is going to go between those two columns, half the load is going to go between those two columns, half the load is going to go between those two columns, half the load becomes one, and therefore this becomes your tributary area. And therefore I take my factored load multiplied by my tributary area, and that's going to give me the PF value that the column has to support. And that's how easy that is, if everything's simply supported. Okay. Now, so The unsupported length of the column is 4 meters. Of course, that you would see from your geometry. In other words, from the floor to the underside of the beam, or from the floor to the top side of the beam, depending on how it's being supported. And of course, we're going to say that it's effectively pinned at both ends. That means K is equal to 1. Now, we factor our loads, 1.25 times my dead load plus 1.5 times my snow load. Okay, and I end up getting 8.7 kp. And of course, if you want to be really conscientious, you should do load combination number 1 also. But I know that in this case here, this is not 10 times that, so therefore this is the one that's going to govern. And now I get my CF value is my fractal load times my tributary area. So I have a CF value of 783 kilonewtons. Okay. Now, what do I need to do? Well, okay, determine. You always have to make sure that CR is greater than CF. In other words, the factored resistance of your section is greater than the factored force that your section has to support. Now, this is the easiest thing to do. I sent you these tables. I apologize for the quality of the tables, but I don't know, when I was scanning this at school, the scanner was reading, these are very flimsy sheets, okay? So this table here, I gave you, for example, all the HSSs, okay? Now this is rectangular. I don't know if you guys can see it, but here there's a C. If you buy the handbook, like these are green pages, and there's like a C here. And if you can't see this, remember that this is for the Canadian one, and this is a class C. Okay, so the class C. Okay, and of course the class C means that they take a sheet of metal like this. Okay, and then they eventually bend it into a HSS like this. That's what a class C means. It's cold form. C is for cold form. And then they seam weld it all the way along. And that's why, and because of this bending, the residual stress is caused by the bending, and therefore it weakens the section. So this is for, and then in this table here, you will have, you start off with the rectangular shapes. And these are all like, the reason why the numbers seem so bizarre, because this is a 4-inch by 2-inch by a 1/4 inch. These are all imperial sizes. They still only mill them in imperial sizes. Then after that, you have square ones. I said to use a class C. So this is where we would be looking at the table. Okay. Now, what you do here is simply say, okay, let me go and get a length of 4 meters and try to find a CR value greater than what I need. So here, they're all way above what I need. So I'm going to go to the next page. I'm going to go to the next page. And I even forgot what was the CR value that we needed. We needed 783. Okay, we needed 783. So for 400, sorry, this is 783. So for 7, I'm getting there. So here I have, for example, this is no good. Yeah, 776, not good enough. Okay. And oh, here I have, I can use a 152 by 152. In other words, I just look for a value. Oh, sorry. I should have done this. Okay. So I look for a CR value that's greater than what I need, 783. And see here, for example, I know this gives me a value greater, but look, this weighs much more than that one. Okay, so I go across, I pick a couple of choices, and I find which is the lightest one that can give me a CR value that's greater than 7. So I have a 127 by 127 by 113. I have here 152 by 152 by, so this one's lighter, okay? And I find the lightest one, and once I've chosen it, okay, so I have a 178 by 178 by 6.4, okay? Even though my CR value here is really high, if I look at the different weights here, 178 by 178 by 6.4. Even though this seems to be higher, if you look at the weight here of 33.4 kilograms per meter versus what you have here, 34.8, and versus what you have here. So even though this looks like a higher C value, because the column is bigger, of course, it gives you a little bit, and therefore this would be the one that you should be choosing right here. So that's why it's just very, very, very similar to the beam selection table. If you want to take the lightest one, you make sure you look at, in that range, out of these three possibilities, which is the one that gives me the, and this is where you see how this is where you get the mass per unit length. Okay, so like I said, this one was good here, but okay, it gave me a CR more than what I need. This one was good here, but you understand, if I look at how much this weighs, and I look how much this weighs, and I look how much this weighs, this gives me even a better CR, and it only weighs 33.4 kilograms per meter, and therefore, like if you choose this one, there's nothing wrong with it. If you choose this one, there's nothing wrong with it. But if you want to try to choose the lightest one that can give you the required resistance, this is the one that you should have chosen. And this is the one that will meet your design criteria and also be the cheapest one to actually, because as far as when this guy that's selling this one, or the guy that's selling this one, or the guy that's, it's all going to be sold for the same, like so many dollars per kilogram, and therefore the lighter your section, the less they're going to be paying for the steel to actually make the steel structure. Okay, so, and we'll go through this table. I just want to go through this table with you at least once. Okay, so here, and of course, so these are all, okay, this is all Canadian. Now you have some round shapes. If you want to use a round HSS, they also have the values for the round shapes, okay? Then they have the class H. In other words, this is hot rolled. And if you compare the two values, like if you want to do this, go take the same size, the same length, take the CR value for a cold form and come back and look at it under the class C hot, like hot versus cold. You'll find that the CR value here is higher than there. And then ultimately, what I like about this one is they give you the American ones, okay? And this is the American HSS. The American HSS are the weaker of the three. And that's because, one, it's 450 MPa, so the steel was slightly weaker. And also, the tolerances for when they make these things are a little bit higher than the Canadian ones, and therefore, because of those tolerances, it makes it weaker. So be very careful. I strongly recommend that if ever you're designing a HSS, okay, square, whatever, always come and choose your size from here, from the American one, A500. And that's why if they happen to put some Canadian steel, you'll only be safe. What I've seen many situations where I was involved, the guy had specified Canadian, and the guy actually bought the cheaper American stuff, and he tried to pass it, and there was a problem, and it ended up being a big issue. Okay, so always specify the American one, and this way, if they don't find any American one and they have to use the Canadian one, don't be worried about it. Those values are only higher than what's here. So that's what you should be using. And it's very similar to the other ones. Start off with the rectangular shapes, then they go to the square shapes, and then they go to the round shapes. So the tables are simply Class C, Canadian Class C. Okay. And don't confuse grade C with Class C. Grade C is their grade of HSSs. They have different grades in the state. Okay. So you have Class C, and that's Canadian, and of course it's A350. Then you have Class H, A350, and then you have ASTM A500 grade C, and that's totally different. So that's, and then of course you have rectangular, square, and round. So that's how the tables work. Like I said, I apologize for the quality of the scanning, but I only realized this after I scanned so many pages. So now you guys have all the three sets in one file. And therefore, oh, that's it. What time? How are we doing time-wise? Are we? Oh, yeah, 1 more minute, guys. We'll have our next test next week. Okay, and so don't worry about columns. There will be no columns on the test. Okay, the only thing, you're gonna have 3 problems. You'll have, I think it's an hour. I worked out I'm going to give you an hour to do the test. Okay, and let me know, do you guys want to start fresh in the morning at 8 o'clock, or do you want to take the first hour to do some tutorial and then do the test afterwards? How do you want to do it?
I like
The
the
Test
tutorial.
tutorial.
afterwards.
Yeah, the tutorial.
Okay, so what we'll do is we'll have a tutorial for about 45 minutes. Is that everybody good with that? And then you guys can have a 15-minute break, and then we'll have the test at 9 o'clock, and then the test has to be in by 10 o'clock. And same thing like with all the other tests, for every minute that it's going to be late after 10 o'clock, you'll be losing a mark, okay? So just worry, no columns on this test, just beams. And I will give there is going to be an assignment that you're going to be receiving. That's only going to be corrected the week after. And then after the test, I'm going to still have a lab period because I want to, it's only going to be about the drawings. So we'll talk about the structural steel drawings in that lab. I think that's what we're going to do. We're not going to do anything new. And I'd like to do a lab after the test. So what we'll do is like we'll go from 9 to 10 for the test. After that, we'll take a 20-minute break, even a half-hour break. I don't care. And then we'll come back at 10:30, and we'll go over the drawing, so you guys can also start seeing like what's expected of you with regards to this. Very similar like we did for wood. We're going to do it for steel, and this way you guys will have a good idea what to do for the steel project. And if you want to get started on them, you'll be able to get started on them. Okay, so listen. Yes,
Sir, I have a quick question.
go ahead.
You know the Excel file for the steel?
Yes, the one I sent you. Yeah, which one?
Yeah.
I sent you another one this morning. Which one are you talking about?
No, the one that you gave us last week
For the Gerber one. Yeah, okay.
for the Gerber one.
Yes.
Were we supposed to do it for today?
You should.
And then we'll
Look, Gordon, I'm not going to pressure you. It's your project. You understand? It's your project. I'm going to be moving along, and I strongly suggest you keep up with the work. Okay.
No, yeah, for sure.
So in other words, if you didn't do it for today, you're going to have to do it for week 15. How's that?
Okay, thank you.
All I'm saying, Gordon, is that I'm not there to. I'm not going to be there. Oh, I want it. You guys are supposed to be in your third year. You're supposed to be adults. You're supposed to be mature. You're supposed to be able to schedule yourselves. You understand? I strongly recommend that you keep up with the labs. Okay, if you don't want to get inundated at the end of the semester. So Gordon, do keep up. Like in other words, if you can find, and this way, if you have questions, we can talk about it during the lab and this and that. But I'm definitely going to talk about Gerber's, like in week number 12. By that time, I'm going to say, wow, you waited this long to start doing your Gerber design. I think you're way behind. You understand? So, Gordon, I do not check where you are with respect to the project. I will move, I will just expect you to keep, if you can maintain the, like when I ask you to do something for next week, have it done. Because like, for example, today, I'm not talking Gerber. I'm talking about perimeter beams. You understand? And then the next lab, I'll be talking about drawings. Then after that, I'll be talking about columns and base plates and so on and so on. You understand? So I just keep moving. You understand? And just keep up with the workload, Gordon.
Okay, thank you.
Sounds good. So, okay, let me just